So, with a solution, you have a solute and a solvent. Now, I want you to look at these two words and count the letters and tell me which one has fewer letters, solvent or solute.
Solute.
Solute, correct. And it's also the one that's the least amount in the solution.
Oh.
And the solvent is the one with more. You might think of a solute being something that's solid, that's dissolved in a liquid, but you can actually have a liquid solute and a liquid solvent. I've never heard of a solid solvent because there's always more solvent. I mean, I'm sure there's got to be some situation where there's one, but that I know of, I don't know of any. So let's say, and then solute plus solution, solute plus solvent is solution. Okay. So if I had salt and water, I would have salt water. It's not really a reaction because the salt's still salt, water's still water. But which one of, let's say I have 4 grams of salt and 182 grams of water. Which one is the solute?
4 grams.
The salt, correct. And this is because there's less of it, so that's the solute. This one, there's more of it, so it's the solvent. All right. So I will tell you about a job that I once had. It was a kind of cool job some days. I say some days because some days I spent all day long reading science papers, and I have to tell you, there's nothing worse than reading a paper written by a scientist. I like to say that it would be exciting or you're going to love it, but that they're mind-numbingly boring. To me, maybe you will love it. And I'm sure if you ask other science teachers, they're going to tell you how fascinating they are. But I've sat down, I've read them and read them and read them. They're so boring. Exactly. Everything after the abstract. And sometimes even the abstract. It depends. And then they seem to like to write in such a way that they want to prove how smart they are by using words no one's ever heard of before. Even other scientists are like, what? And it would make sense to just, exactly, to just explain it so people understand it, because that's the whole purpose of writing, is to convey a message. So it's not something that I love. For 5-year-olds, I probably would like a science paper like that. They actually have a book called Quantum Physics for Babies. Kind of like that book. All right, so in this job, yeah, they really do. They have a whole like little whole set of science for baby books. It's completely nuts. But they're cute. I don't think a baby would understand them, but you could read it to a baby, you know, if you wanted to. So in this, we had ash. And this ash came from coal, C-O-A-L, that was burned at the electric company. So the electric company burned the ash. Some ash flew up, some ash flew down. Shockingly, the ash that flew up was called fly ash, and the ash that fell down was called bottom ash. Such amazingly creative names. Exactly. So the fly ash is what we studied because you can use it in concrete to replace some of the cement that you have to use. Because concrete is rocks, sand, cement, and a soap-like substance. And the soap-like substance is to make the bubbles in the concrete so that when it gets cold, if there's any water that's down in the concrete, it will go into the little holes that the bubbles have made and expand without cracking the concrete. Let's see. This is supposed to be the word coal. That's a good question. All right. So, and all of this stuff is not going to be on your test. I'm just getting to a point. So anyway, the EPA said that there's too much mercury going out into the air, so they wanted activated carbon to be put into the fly ash to capture the mercury, which is great, but it makes it useless for making concrete. There were lots of businesses that relied on it being put into the concrete. Concrete companies were using it because it was cheaper than cement. Fly ash companies sold it, and electric companies sold it to the fly ash companies. And so there were people making money off of it, but all of a sudden it couldn't be sold like that because activated carbon would soak up the air entraining agents, which are the soap-like substances. So that's where my job came in. So we wanted to treat it by putting a substance on it. So we wanted to spray it. But we needed to know how much was on there. And every single ash set that you get is different because the coal is different that comes out of the ground, even if you get it at the same place because it's natural. So we had to find some way to measure this. We wanted to know the point where we filled up all the holes in the activated carbon, but did not have extra, because extra would make the concrete no good. So we found out that the spray that we put on the ash was fluorescent. So they had a fluorescence machine monitor built special for this ash, and my job was to work with the first to find what spray should we use, and then to help build the machine and figure out why it breaks occasionally and these kinds of things, and then to develop the test for this. So when I developed the test for this, the first thing I had to do was build a calibration curve. And this is actually in the textbook, so calibration curve is important. So for the calibration curve, what I needed to do was take a bunch of sets of solution and put a known amount of the spray in each one. So I needed to have something with, like, let's say 1%, and then 2%, and then 3%, and so forth, so that I could build a curve so that, let's say, this one produced a certain amount of fluorescence. Let's say the machine read 128, and this one read 534 or whatever. So as you put the spray onto the ash, and then you mix it with water, then you put the fluorescence probe down into the water to see if there's any leftover spray, because we don't want any leftover. So if there was leftover, we could find out what percent was left over. And that was based on the calibration curve, because we had measured 1% gives you this reading, 2% gives you that reading, and so forth. So then we would say, okay, well, here's our reading. So we come up here, and we find out that was like 4% or something like that. So then we find out how much, too much it is. So we figure out how to dose the ash. So to do that, you have to have a calibration curve. And you have to have a way of measuring what amount of solution you have. Now, the type of calibration curves and standards. These would be considered standards because those I know exactly how much spray was in each one. So standard, you know how much is in each one. And then most of the time they start out with a concentrated, and then they dilute it, and then they dilute it, and they dilute it to a known amount. So maybe they start with 3%, they dilute it to 2%, they dilute it to 1%, and then they measure each one of these. That's how you measure the standards, that's how you make the standards, and that's how you build a calibration curve. So looking at that, well, clear, okay. We've got concentrated and dilute. And these are relative to each other. So let's say that I have Kool-Aid, the powdered kind with the sugar in it, and I give it to a 5-year-old and I ask them to make me a really good glass of Kool-Aid. They will probably put a ton of Kool-Aid in there. And I'm going to think to myself, it's concentrated because there's a lot in there. The child may think, well, I only put half the Kool-Aid I normally put in there, so they would think that it's diluted. So it really depends on what you're comparing it to. So they're comparing it to a more concentrated solution. So compared to the more concentrated solution, to them, it's dilute. To me, I'm comparing it to a less concentrated solution, so I consider it really concentrated. So the only thing you can really tell with these words is that there's either a lot or a little when comparing two different solutions. That doesn't tell you a whole lot. So that's why we came up with units for concentration, so you know exactly how much. So we have molarity, and it equals moles of solute per liters of solution. And this symbol stands for moles, so that you can kind of, when you see the formulas, you kind of get an idea of that. And then let's say you're diluting a more concentrated solution. So let's say you have 5 liters of a 2 molar solution, and you want to convert it to a 1 molar solution, and you want to know like how much you're going to end up with. You would use a formula like this: M1 V1 equals M2 V2, or M initial V initial equals M final V final. So this is like, how much of the first solution do I need in order to get a certain volume of a certain concentration of a second one? So, for example, let's say I have this 5 liters, 2 molars, 2 molar solution, and I want to make a solution, but I don't know what volume I'm going to end up with. So then I would do 5 times 2 equals V2 times the molarity, which is 1, and then solve for V2. And so that means my more dilute solution would be 10 liters if I used 5 liters to cut the solution concentration in half, which makes sense. So if you double the amount of water, then you would get half as much concentration. One thing to keep in mind, though, as you dilute these solutions, let's say I have 6 moles in this flask, and I had, 6 milliliters. and then I dilute it, and I have 12 milliliters. How many moles do I have in there now? 6, correct. I have the exact same amount of moles as I did before. I just have more liquid. And then if I diluted it again, I would still have 6 moles. You don't have any more moles of solute until you put some more in there. But most of the time when they dilute things, well, all the time when they dilute things, they just add more and more solvent. And then that brings the solution down. It's still 6 because let's say I have a flask, and in my flask I put 6 pennies and 1 liter of water. And then I take the same flask and I still have my 6 pennies and I add an extra liter, so now I have 2 liters. I still would just have 6 pennies because I didn't do anything different to the pennies. And it's the same here because I didn't do anything different with the amount of solute. So let's say my solute was sodium chloride. And in this one, I don't add any more sodium chloride. I just add more water. Then I would still have the same amount of sodium chloride. Not the same concentration, but the same number of moles. Because my concentration will change if I add more more solvent. All right, and let's see. We'll do some examples if we have time to. I'm hoping we do. You also see it written like this. C1V1 equals C2V2. And this just means concentration 1, volume 1 equals concentration 2, volume 2. And so that way you could use ppm or millimolar or something like that. Sure. Okay, so what's the final volume in milliliters of a solution if you have 35.5 grams of ammonium nitrate and want a concentration of 1.25 molar? Okay, so the first thing we want to do is find out how many moles of ammonium nitrate we have. So we're going to convert that. So we need the molar mass of ammonium nitrate, and nitrogen is 14. And we have 2 nitrogen in there, 1 in the ammonium part, 1 in the nitrate part. So 1 here and 1 here. And then we have 4 hydrogen. And then oxygen we have 3, and each one of those is 16. So this is 48, 4, 28. That would be, let me do them 2 at a time, 28 and 4, 32, 48, thank you, 80. All right, so it's 80 grams of NH4, NO3, 1 mole, NH4, NO3. All right, so somebody calculate that and let me know how many moles of ammonium nitrate we'll have. 0.44. All right. And then, let's see, final volume in milliliters of solution if you have 35.5 grams NH4 and want a concentration of 1.25. They gave you the final, okay, the final volume. I was like, they gave you the final concentration. Okay, they want that. All right. So, interesting. Okay, so in this one, we're not going to be using this kind of thing. We're just going to use this formula. Molarity equals moles over volume. So this is how many moles we have. We don't know the volume. We do know the molarity is supposed to be 1.25. So we have this part and this part. We're just going to solve for volume. So to do that, I'm going to multiply both sides by V. Let me change colors so you can see what I'm doing. And that'll make it like this, 0.44 moles NH4NO3 equals 1.25 V divided by 1.25. And so what is 0.44 divided by 1.25? .35. So that would be in liters because molarity is moles per liter. So we wanted milliliters, so you multiply by N is moles. So we're going to multiply by 1,000 to get milliliters. So that would be 350 milliliters is the volume. Does that one make sense? Why is the moles on the left side? You could put it on the right. Here, give me just a second. I'll show you. Okay, so you could write molarity equals moles over volume, or you could write moles over volume equals molarity. It's the same thing. So it's whether or not you feel like putting it on the right or the left. Doesn't matter which way. So yeah, so it would have put 0.44 here, and then solved for the volume. Yes, there will be similar problems. And I didn't rearrange the formula, but let me show you how you would do that. So if I want to know the volume, I'm going to multiply both sides by volume to get it out of the bottom. Now get volume by itself. And volume equals N over molarity. All right. Molarity is not the final volume. Molarity is the concentration. The final volume is different from that. Correct. Oh no, I divided number of moles by the molarity. Yeah, molarity was given in the problem. So the molarity was 1.25 molar. So we were given that. And then we had solved to find out how many moles were in there by converting the ammonium nitrate to moles. So we were given that it was 0.44 moles. And we don't know the volume. So if we do N over V equals M, it will be 0.44 over V equals 1.25. And then just solve for V from there. Does that make more sense? Okay, good. All right. All right. So that brings us to Beer's law. Oh, but before we go there, I just wanted to remind you about this one. C1V1 equals C2V2. In that one, you don't have to use molarity. You could use millimolar. You could use ppm. It doesn't really matter. Just make sure that whatever concentration you have there has the same units as concentration there. It's the same formula basically as M1V1 equals M2V2, except they specify that this is molarity. And here they don't specify what the units are. All right, so Beer's law. We've got A equals E, B, C. Most of the time you see it written like this. A equals A, B, C. And so the first one here is absorbance. And then this is molar absorptivity. This is the path length of the cell, and I'll explain that in a second. And that's usually in centimeters. And C is concentration and molarity. And so once you've got that all written down, then I will explain the experiment that goes along with this. I'll give you just a second. All right. Anybody need a second on this? No? Okay. So, all right. So we've got absorbance equals absorptivity times path length times concentration. Or as you'll often see, like that. So let's say we have a solution and it's Kool-Aid and it's blue raspberry. And we have a solution that is dark blue. And we want to find out the concentration of Kool-Aid in the solution. And we don't know the concentration. So what we would do is first we're going to build a calibration curve with known concentrations. So maybe we'll start with a 10% solution and then go to 5% and then 2.5% and then 1.25%. And then we'll measure all of these. Now, the molar absorptivity is a constant that depends on what material you have. So either you'll be given this number in the problem or you'll solve for this number in the problem. But it's not a constant you can remember because it changes depending on what substance you're using. All right. So what we have is we have a machine and we have a little, they call it a cuvette. It's a tiny plastic or glass rectangle, and the top is open and you can put your sample in the rectangle. It doesn't really matter how much sample you have in there as long as you have enough. So generally you want to fill it up pretty high, but you don't want to, overflow it. And then you want to make sure you dry all the drops off of it so that it's dry on the outside and has your sample on the inside. You drop the cuvette down into the machine and then you close it. It'll have a lid that comes down over the top so that the cuvette will be in the dark. And then you have a source, which is for light, and it will shine light through the solution. Oh, have you? Cool. Anybody not use a spectrophotometer? Okay. Okay, so a couple people haven't. All right. So the light source goes through the cuvette, which has your sample in it, and then on the other side is a detector, and it detects how much light there is. So your sample will absorb some light. And depending on how much light is detected over here will tell you how much light was absorbed. So let's say you have 100 lumens, and then you pass it through your source, and then it detects 80 lumens, then it means 20 lumens was absorbed, which would actually be a lot to absorb, but just, so you have some sort of amount there. So the absorbance is a measure of how much light is absorbed, or the intensity. It's a measure of the intensity of the color of your solution. So in our situation, we'd want to know how blue is it, and the answer, how blue is it, is kind of given by absorbance. And then the path length is the path length across the cuvette, and that's usually in centimeters. And then C is molarity. So in these, which are the knowns, we would know the concentration. So then we would build a curve, and then we would take our unknown, put it in the machine, and get a reading. And let's say the reading was here, landed on the curve there, we come down, and we find out that it's 3%. Then that's how we would find the concentration of our solution. If it was sodium chloride where it was colorless, you would use something different. You would probably use, you could possibly use a pH meter, but it's not going to change the pH much. More likely, you would use something that would measure electric current. And depending on the electric current that's going through it, that would give you an idea of how much sodium chloride is in solution. So if it's colorless, you'd have to use something different. All right. And in the book, it gives you a picture of a spectrophotometer, which if you've used one before, you will recognize it. And then they show you a cuvette, and they kind of explain the experiment there. Then they give you an opportunity to apply Beer's law by doing a practice problem. Now, I want to do some practice problems with solution concentration. Let's see what time it is. Oh, I have 4 minutes. Yay, I can do one, which is my favorite one. I have to decide quickly. Okay, we did one of those already. We did the same thing already. Ah, good. All right. This is going to be an M1V1 equals M2V2 problem. So it says, how do you prepare a 3-liter, sorry guys, a 3-liter solution that's 0.500 molar calcium chloride from a 10 molar stock solution? The stock solution is always what you start with. It's always more concentrated. So if that's what we start with, that's M1. And it wants to know how to prepare it. We write down all the other stuff that we know. We know that in the end, we want it to be 0.500 molar. And we want to have, and it's calcium chloride, we want to have 3 liters of it. So the only thing we don't know is the initial volume that we need to take out, basically. So if we're making this solution, we're going to start with this bottle, but we need to know how much of that bottle do I remove before I can bring up the volume to 3 liters. So that's what V1 is how much of the initial solution do I use? So that would be 10 V1 equals 0.5 times 3. So this would be 10 V1 equals 1.5 divided by 10 divided by 10. So V1 equals, I think, I'm doing this math in my head, 0.15 liters, or 150 milliliters of the initial solution. So then we have a flask. We have our stock solution. So from our stock solution, we put in 150 milliliters. And we have let's say we're using a volumetric flask that actually has a different shape than this, but we're using a volumetric flask that only has one mark on it, and it's exact. And let's say we're using a 3-liter volumetric flask. So we put our sample in there, and so we have a teeny tiny bit of our sample. Then we put water in until it reaches this mark here. And then we cover the top and mix it. If you don't mix it, then the top's going to be all water and the solution's still going to be at the bottom. So you're going to mix it, and then you'll have 3 liters of 0.5 molar calcium chloride solution. They give you that for the, well, this is the initial, not the initial volume, but the initial concentration. So this is concentration, so that's molarity. This is molarity, so those two are given. This is the volume of the final solution they want. That's given. The only thing they don't give you is the initial volume. So that's what you have to solve for there. All right. Well, that's all I've got for you guys. And I'm ending at 11, which is amazing. So, cool. You're welcome. I will see you guys on Monday.